Here we have a spectral data set. Each line in the plot below is a spectrum, a near-infrared spectrum of tablets for which we want to determine the water content. We have 47 samples, each measured in replicates, so we have 94 different spectra in the plot. There are 780 variables in each spectrum, and then we have 94 water concentration, so we only have one Y variable in this case. We get a model and we look at the model, and here we see a score plot. We can see in this score plot that there seems to be a problem with some of the replicates. We know that the samples are replicates because we made them ourselves, but what we see is that sample 5 and 6, which are replicates, are not lying close together, and sample 3 and 4, which are replicates, are not lying close together. So there must be some kind of problem with these. That can lead us to plotting the raw data again and looking specifically at some of these samples. If we do that, we get a plot like this, for example. We can see sample 1 and 2, those are replicates, and their spectra are very, very similar. But if we look at sample 3 and 4, we can see that their spectra are not at all similar. So there must be some kind of problem here, and that we have to go back and look into in order to figure out how we can handle this. We will not do that here, but this is clearly something that must be handled. But for now we will simply remove these samples as outliers. When we look at the variance explained from cross-validation, we can see that there is a big dip after 4 components, and then not much is happening. That shows us that we don't explain much additional variation in Y in the water content using more than 4 components. So 4 components would be the optimal model complexity for this model. And that makes it possible for us to make a prediction plot using 4 components, and there we can see that we get a fair prediction. Whether it's good enough depends on the application and the requirements from the application. In the left upper part of the prediction plot we can see some characteristics of this prediction plot. We can see how many elements there are, and we can see the correlation and the RMSEP. And remember that the RMSEP, the average error, would be the same units as our original measurement. We can see on the x-axis that the original measurements span from 0.2 to 1.2, and we can see then that this error is fairly small. Also notice that correlations are always intriguing, but you cannot assess and compare different models from their correlations. Correlations tell you something about the linear relationship among the samples that you use, but if you remove half the samples, it's quite likely that your correlation can change in one or the other way, no matter if your model improves or worsens. Never look at correlations for comparing different models, unless you have exactly the same samples in the 2 different models. Finally, let's just have an overview here of all the different items that you can plot when you have fitted a PLS regression model. We have gone through all these plots, but here's just an explanation of what they are. Before we end, just a short discussion of some of the alternatives to PLS. First and foremost, we have something called multiple linear regression. In multiple linear regression, you find the regression vector B directly from your Y and X values by simply dividing one with the other. Well, mathematically it's not a division, but essentially that's what it does. This only works when you have few variables, and few variables mostly means much less than 10 variables. It also means that you should not have any severe collinearity, that is, variables that are correlated significantly. Then the multiple linear regression will not work. MLR is used a lot in classical data analysis, but it's not used very often when you do multivariate data analysis. One good reason for not using it is that the PLS regression method will give you the MLR solution if you extract all the components you can. So essentially, when you do a PLS regression, you already have the MLR solution, and your cross-validation or your validation will show you that you need that in case you do. Then the validation will show you that you need all components. So therefore, there's no need to think too much about whether you should go for an MLR regression. The validation will show that automatically. Another alternative to PLS is what is called principal component regression. That's a simple principle. You take your X data and do a PCA on that. That will give you a score matrix T, which represents your X. So if you choose enough components, then the T will represent all the systematic variation in X, and therefore you can use T instead of X for building a regression model. And in fact, you can use MLR to build that regression model, because you know now that you have few variables from your PCA, and you know that they are not correlated because scores from PCA are orthogonal per definition. There's a lot of religion about whether to use PCR or PLS. But what practical experience shows is that there's rarely any difference between the results you get. One practical difference is that in some situations you need fewer components with PLS than with PCR. That is convenient in some situations because it's easier to interpret and explore and validate your model when you have fewer components. But essentially you would mostly get exactly the same predictions with a rightly validated PCR model or a PLS model. Before we stop, then a last slide, which talks about the difference between multivariate and univariate regression. In univariate regression, we only use one variable instead of many. What's the advantage and disadvantage of doing that? Well, first of all, we need to have selectivity. If we want to predict something from one X variable, well then that X variable must reflect only the property of interest and nothing else. That also means that we cannot have interference, that is, signals from other properties that overlap X. We don't have any outlier control in univariate regression, not from the data themselves. There's no way that we can check whether an X value is appropriate or not. We can check if it's within limit, but if it's within limit, that's all we can do. The main advantage of univariate regression is that we typically need only few samples to build a model. In multivariate regression, we don't need selectivity anymore. The signal of our property that we're interested in can overlap with many other signals. As long as we include many samples, which have varying degrees of these interfering signals, then we can handle that mathematically. We also have outlier control. We can tell if a sample is different or not. We have good graphics, and that's important. The drawback, though, is that we need many samples in order to build a model, depending on the complexity of the problem.